Waiting for recording to start. Okay, I think we're in business. So this lesson is on electron configurations. So electron configurations are it's a model that we use to describe the electrons in an atom. Let me pull up a periodic table real quick. All right, so here is a periodic table. We have learned that the periodic table is arranged in terms of increasing atomic size. We've also learned that things like the atomic number, the mass number, the average atomic mass give us information as it pertains to how many subatomic particles we have for each atom. The chemistry that we are studying is pretty much the study of electrons from here on out. Okay, electrons are the meat and potatoes when it comes to element interactions. We had a very short little quip about nuclear chemistry, but that's kind of a one and done section. Any further, if we went deeper into that, we'd be going into physics. And so chemistry truly is the first understanding the properties of matter. That's how we started this course. And then we transitioned to learning what atoms were. And now we're going to be studying the interactions between atoms. And those interactions have everything to do with the electrons. So if those interactions have everything to do with the electrons, it's very important that we're able to talk about specific electrons in each type of atom. And so the model that we're going to be learning today will teach us how to isolate and talk about very specific electrons for each element. So that is the goal of electron configurations. So we're figuring out how electrons are configured for each atom. We already have some sort of idea in terms of their configuration. We know that we have the Bohr model, the stepladder model, where we have electrons at different levels. The higher energy levels are further away from the nucleus. The lower energy levels are closer to the nucleus. But we also learned that his model did break down when it came to things like discontinuity between those different steps. And so the most recent model is the Schrodinger model. And that model, I think from 1924, talks about how electrons are in regions around the nucleus that we don't really know the location of them. So instead, we define regions in which they have a high probability of being. So that's our goal here. So 1922, I might have said 24, Erwin Schrödinger, he analyzed electron orbits in an atom from a geometric point of view. And at this point, we transition from using the term orbit. An orbit is just a circle or an ellipse around something. So as something moves around something else, that is an orbit. So we are in orbit around the sun. The moon is in orbit around the earth. It was believed that electrons were in orbit around nuclei, and we still believe that. However, because we can't define that orbit due to the observer effect and the Heisenberg uncertainty principle, instead of orbits, we are now defining these regions as orbitals. Let me get a bigger font here. Bigger. There we go. Orbitals. So orbitals versus orbits. I actually started constructing your test already, and I do believe I added that as a question. What's the difference between orbits and orbitals? So orbitals are these regions, and they are just a step above orbits in that we are being more comprehensive in where we can expect to find electrons. And so this is an iteration of his wave function with all the variables that can be plugged into it. So this is a good way of understanding orbitals. So here is an electron density map. And what this electron density map shows is it shows the probability of finding electrons in certain spaces surrounding the nucleus. As you can see that for these electrons, the probability that these electrons are found closer to the nucleus is greater than if they were found further away from the nucleus. And so that's kind of what we're describing with these orbitals. We're describing those regions in which we can expect the electron density to be, where we can expect these electrons to be at. So in order to define the boundary of an atom, if we were able to shrink down to the size of an atom and be able to observe the boundary of an atom, we would be fuzzy. And that's our current understanding. It's not going to be a rigid outside to the atom structure. It's not like a cell. A cell has a membrane, and we can say, oh, there's the cell membrane. That's the outside of the cell. We can't do that with an atom. Instead, we have these clouds of electron density, and it gets denser as we go towards the nucleus. So this abides by the uncertainty principle because we are not pinpointing the location of these electrons. We're just saying where they have the highest probability of being. So let me actually just get you the link here. If I just Google Orbitron, this is a gallery of the different types of orbitals that we could see. And you can see some of them are very complex. And we're going to learn about how we can determine which electrons are occupying which ones and in what manner. And so that's where this image comes from. So this just shows that where we can expect these electrons to kind of be. One general trend that you can see is that, actually, I'm not going to go there yet. So for example, here is a neon atom. Neon is atomic number 2, 4, 6, 8, 10. I just counted these arrows because they symbolize electrons. So neon is number 10. If you look on the periodic table, you'll find that it's atomic number 10. And we know that protons and electrons in a neutral atom should cancel out. So if we have 10 protons and it's atomic number 10, then we should expect 10 electrons. You can see that if I were to show the nucleus for this model, it'd be right in the center. It'd be very small and dense. And then the space surrounding the nucleus, we kind of have these layered clouds going on. Depending on which electrons we're talking about, we can expect their density to be in one of those layered clouds. The inner electrons, because remember, think about the Bohr model, the stepladder model, the inner electrons closest to the nucleus, we typically find that they're arranged in a spherical cloud. As they move further out, they're going to be in these peanut-shaped clouds that are at different angles. So you can kind of see those. And we can also have, so the next layer of electrons as we move further out, we're just going to have a repeat of this pattern. So here we have the smallest circular cloud, and then we have those peanut-shaped clouds right out on the outside of that, and then we have this larger circular cloud. So we have layered orbitals. So this is a good way to visualize what's going on. So from here on out, when we describe the electrons in atoms, we are most concerned with the outer electrons. Because here you can see that this spherical, what's called the 2s orbital, it is enclosing the other smaller ones. And so if we were to talk about the interactions of this atom with another atom, what's going to interact first? Well, it's going to be the outermost electrons because they are the furthest from the nucleus. They're the most loosely held and the most likely to interact with an adjacent atom or molecule. And so the ones on the outside, the highest energy level, are the ones that we are the most concerned with. And when we describe the electrons in the atom, that's what we're describing, is that last outer layer. And so if I go back to this image here, well, this is actually very low res, but you can kind of see the different stacked spherical orbitals in here. And if you look closely, you can see the stacked peanut-shaped orbitals in here. And you can just see that they're all kind of just stacked in each other. And so when I look, so you'll notice that this is the shape of the periodic table. And the reason for that is because we're talking about the greatest or the outermost electron cloud, also sometimes referred to as a shell, electron shell. Okay, so next, we can describe these electrons, or we could locate these electrons with 4 what we call quantum numbers. Quantum numbers are kind of like an address. You have a street number. You live on a specific street. That street is in a town, and that town is in a county. So you have 4 levels of classification, and we could pinpoint exactly where you live, provided that we have all 4 of those levels. So I could say, okay, I live in Fairview. So that's the first level. The next thing I could say is, well, actually, I should have went one level bigger. I should have said, I live in Erie County. That's the broadest level. The next level would be, I live in Fairview. So I'm more precise. I'm talking about the town. If I want to be more precise, I live on Bear Creek Road. Okay, that's even more precise. Oh, my house number is 100. Okay, so I've pinpointed exactly where I live. Therefore, I could. That's kind of what we're doing with electrons. We're narrowing it down where the principal quantum number n is the most broad. That's the county. The azimuthal quantum number L, you'll notice that they use cursive because this looks like a 1. So they use a script or cursive L instead. That's the azimuthal quantum number. That's narrowing it down a little bit further. Then we have the magnetic quantum number. This is M sub L. And then we have M sub S, which is the spin quantum number. So we have 4 quantum numbers that narrow down exactly where these electrons are within an atom. These 4 quantum numbers also describe different things about these electrons too. So you will need to know these quantum numbers as well as their symbols. So you should be able to say, okay, the principal quantum number, the symbol is N. The azimuthal quantum number, the symbol is L. The magnetic quantum number is M sub L, and then the spin quantum number is M sub S. These are the descriptions of what we're actually labeling. So N, the principal quantum number, this is the electron energy level or shell number. So when we were talking about the Bohr model, so let me do a little sketch here. So here is the nucleus. We had the N equals 1, the N equals 2, the N equals 3, 4, 5, 6, 7, blah, blah, blah. Okay, those 7, 6, 5, those levels that we were using previously with the Bohr model, sorry for that awesome sketch, those previous energy levels, that's what we're talking about here. The principal quantum number corresponds to that energy level, that shell. Okay, energy levels can be 1, 2, 3, 4, 5, 6, or 7. As far as we know, we are not aware of any 8th energy level for electrons in an atom. If we have electrons added in the 8th energy level, we have an extremely unstable atom and it decays. So that's kind of our understanding with that. If you look at a periodic table, here are my levels. 1, 2, 3, 4, 5, 6, and 7. That is to say that the outermost electron in francium is in the 7th level. That is to say that the outermost electron in silver is in the 5th energy level. That is to say that the outermost energy or the outermost electron in magnesium is in the 3rd energy level. Just because I'm describing the outermost electron, doesn't mean that all the other electrons aren't important, nor does it mean that they're absent. If I'm describing, let's say, barium atomic number 56, its outermost electron is in the 6th energy level. It's going to have 56 electrons, though. It just happens to be that the 56th one is in the 6th energy level. Also, the 55th one is in the 6th energy level. I know that because cesium is the same thing as barium, but 1 more proton, 1 more electron, and some extra neutrons. So if this is 55, so the 55th electron is in the 6th energy level, the 56th electron is in the 6th energy level, the 72, the 73, 74, 75, all these electrons are in the 6th energy level, the 6th shell. That is what the principal energy level is. 1 through 7. We'll get to this note in a little bit. The next one is the azimuthal quantum number. This describes the orbital type. So that last electron for that atom, what shape is that orbital? Is it a sphere? Is it peanut shaped? Is it a double peanut shape? A donut? Is it just really funky? These are your available shapes. Spheres, peanuts, double peanuts, and peanuts with donuts, and then just plain funky ones. White. These sphere ones are called s orbitals. These peanut ones, I'm being deliberate in describing these shapes. These peanut ones are your p orbitals. S for sphere, P for peanut. These ones over here are your double peanut. Look at how we have the crisscross peanuts down here. Or you could say dumbbells too. These are dumbbells as well. I wouldn't use dumbbells. I would say double peanut to get that D, because those are D orbitals. Also, you'll note some of them have donuts, also starting with D. And then down here are your F orbitals. Funky. They're freaky. There's a lot of stuff going on with these ones. These are the most complex shape. So the F is the most complex, followed by D, P, and then S is the most simple. Spheres, peanuts, double peanuts and donuts, funky. F. S, P, D, F. Kind of a meaningless memory hook, you could say, oh, SPF, what's the SPF on the sunscreen? Oh, duh. So D, SPF D. Okay. However, I would, instead of doing SPF D, I would switch the order DF. Because D is less complex than the F. So what's the SPF on that sunscreen? Oh, duh, it's right here. SPF D. Sphere, peanut, donut, double donut or double peanut, and then funky. Okay, so that is the azimuthal quantum number, the L quantum number. S, P, D, and F are your orbital types. Okay, so keep on reminding yourself, we're talking about electrons and where they're located. So what energy level? 1, 2, 3, 4, 5, 6, 7. Think about the Bohr model. And then what cloud shape are they in? That's your azimuthal, SP, D, or F. And for the SP, D, or F, we code these. The S, we codify it with, I have white font, that's not going to do. We codify the S with a 0. We codify the P with a 1, D with a 2, and F with a 3. 0, 1, 2, 3. Oh, it's right here. Nice. Well done, table maker. Next up, so getting more precise with our electrons, is the magnetic quantum number, the orbital subtype. Let's go back up here. So you can see that, for example, these p orbitals here, here, And here, those p orbitals are aligned on different axes. We have them aligned on, shouldn't have done dotted lines. I have them aligned on the y-axis, the x-axis, and the z-axis. So typically in a coordinate plane, you have your x and your y. So that's why we're labeling these x, y. So if we have two orbitals aligned perpendicular to one another, then we have one aligned along the x, one aligned along the y. If we have one that's perpendicular to the other two, so 3 dimensions, then we have what's called the z axis, and that's coming towards you. Okay, so x, y, that's your typical coordinate plane that you're used to in math class, but we're adding one more because we're dealing with 3-dimensional atoms, and that's the z coming towards you. So now we have our energy level, that's the principal quantum number. We have the shape of the orbital, that's the azimuthal quantum number. And then we have the magnetic quantum number, which corresponds to the orientation of that orbital. So we have the size, the energy level, the shape, as well as the orientation of that shape. So we have 3 different levels of where these electrons are at this point. So principal, azimuthal, magnetic. For your magnetic quantum number, these will always have the number of, how do I explain this? A sphere. Let's start with a sphere. So an s orbital is a sphere. If I were to orient that along the x-axis, if I were to orient that along the y-axis, and if I was to orient that along the z-axis, would there be any difference? A sphere is symmetrical in 3 dimensions. So therefore, if I orient that sphere along the x, y, or z, I'm not going to be able to tell the difference because it's symmetrically the same in all 3 dimensions. So therefore, my orientations available for an s orbital are 0. I have 0 orientations available. Well, I shouldn't say that's not the number of orientations. That is the orientation that is available for the s orbital. The p orbital, I could have it oriented on the x, the y, or the z axis. To code that, I can say that the p orbital can be on the x, -1, the y, 0, or the z axis, +1. So these are the 3 orientations available for a p orbital. If I take the L quantum number, the options for the M sub L orientations are -L. So this is the code, -L, -L plus 1, then however many you have, all the way to 0, then this is wrong. Don't write that. Sorry. It's going to be -L, 0, +L. So here is the -L. So L is 1. So -1. And then 0. And then +L. So L is 1. So +1. What are the orientations available for D? D or the double peanut or the peanut with a donut. There's a lot of orientations available for D. To determine my options, I start with my L quantum number and I say, okay, make it negative. So -2. The next one is -1. The next one is 0. Next one is 1. Or I should write the positive. Positive 1 and positive 2. Do we see the pattern between this one and this one? Go ahead and write the orientations for this F orbital. What are the possible orientations? Continue the pattern. I can start you off. -3, because it's negative L. Oh, I skipped one. Okay, so -2, -1, 0, +1, +2, and +3. It should make sense that as the orbital shape gets more complex, so does its orientations. So we have the energy level, N. The type of orbital, L. The orientation of that orbital, M sub L. So we're building an address for each electron. So all of these notes here are what this is talking about. Okay, here's the last thing. The final piece of information to locate exactly one electron. One orbital can hold 2 electrons. Okay, one orbital can hold 2 electrons. And with these first 3 numbers, I'm pinpointing that orbital. What energy level are we dealing with? So how close or how far away from the nucleus? What shape of orbital am I dealing with? What orientation of that orbital am I dealing with? So now I've narrowed it down to the exact orbital I'm going to find that electron. But as soon as I check in that orbital, which you can't because of the uncertainty principle, but as soon as you check in that orbital, you're going to find there's 2 electrons there. And because electrons are negatively charged and repel one another, in order to share that orbital, they need to be spinning in opposite directions. If they are not spinning in opposite directions, they will repel one another. So they have to be spinning in opposite directions. And so the last thing that we could do to pinpoint an exact electron is to describe which spin or which direction they're spinning. Are they spinning up or are they spinning down? Up, we code with +1/2, and down, we code with -1/2. So up spin is +1/2, down spin is -1/2. Yes. They have to be spinning opposite direction. Same thing. So they're in the same orbital. They are paired. So they're one and the same. So we have M sub L. That's the magnetic. M sub S is the spin. So N, L, M sub L, and M sub S. Here's where it starts to come together, hopefully. This region of the periodic table, the first two columns, is called the S block. It is called the S block because the outer electron for each one of these will be in a spherical orbital. In other words, we are dealing with the second quantum number of 0. Everything in this block has a second quantum number, an azimuthal number of 0. And I can assign the first two quantum numbers of all of these ones. So, for example, hydrogen, first energy level, so n equals 1, and it's an S-shaped orbital, so L equals 0. So those are the first two quantum numbers for hydrogen. For this lithium and beryllium, again, we're talking about the outermost electron. All the other electrons have their own addresses, and these atoms have those electrons too, but we're only talking about the outermost electron, the highest energy electron. So the second energy level has an n equals 2, and the shape, we're in the S block, so the shape is 0, sphere. Here's our dilemma. If I give you these two numbers and I say, okay, go find the electron that's at the location 2, 0, you say, okay, easy. Second energy level, okay, that's this row here. And then the shape of the orbital, 0, that's the S block right here. But wait, now I have two elements. So now I need more numbers to narrow it down. Well, what are the possible orientations of a sphere? Possible orientations are here. Oh, there's only one orientation for a sphere. So the third quantum number is kind of still stuck with 0. So I can give you the first three quantum numbers of these, and I still haven't narrowed it down to lithium or beryllium. It's not until that last quantum number that I provide do I arrive at what element I'm talking about, what last electron I'm talking about. So this address, 200 positive 1/2, is lithium. Beryllium has the address 200 negative 1/2. Can we finish out hydrogen? 1, 0, only one orientation, 0, and then this is going to be positive 1/2. Positives come first, negatives come second. So all of these ones in column 1 are all the positives. All these ones in the column 2 are the negatives. We'll see. We'll see. As a test, provide the 4 quantum numbers for cesium, please. So 55. Please write the 4 quantum numbers for cesium. First quantum number is the energy level. So I'm in the 1, 2, 3, 4, 5, 6th row. So therefore, the first quantum number is 6. I'm in the S block. So the shape is a sphere. So we code that with a 0. So the energy level is the principal. So that's N. We're in the 6th. So 6. The shape is an S. We code that with a 0. So 6, 0. This whole area right here is the S block. So 6, 0. And now all the first ones are positive 1/2. Oh, the orientation. Orientation has to be also 0 because the orientation options for a 0. So the orientation options is there's just one, and that's 0 because it's a sphere. It's 3-dimensionally symmetrical. So 6, 0, 0. And then all of these first ones are the positive 1/2 spins. All the second ones are the negative 1/2 spins. So if we're dealing with cesium, it's going to be positive 1/2. Please raise your hand if you had 600 positive 1/2. Okay, good. Let's try another one. Let me introduce you to the next block. So the simplest block was the S block. The next one is the P block, and the P block is over here. There is your P block right there. By the way, helium goes right there for the purposes of this lesson. On the actual periodic table, we do not put it over there. And the reason why is because its reactivity is most similar to neon, argon, krypton, xenon, and radon. Yes?
Helium's in the S block?
Helium, for the purposes of electron configurations, is in the S block. Yes. Okay, let's try one of these. So we have our energy levels still. 1, 2, 3, 4, 5, 6, 7. So we could very easily get the first quantum number, n. The second quantum number is the shape, remember. So we're in the P block. So let's take a look specifically at silicon. My blue square is not very poppy, so let's get white, I guess. Need red. Red will do. Okay, so let's look at silicon. Silicon quantum numbers. First one, 3. We're in the third energy level. Shape is P. P is 1. So the second quantum number is 1. Orientation. Orientation can be -1, 0, or +1, depending on whether it's centered on the X, Y, or Z axis. These are all -1. These are all 0. These are all +1. All of those have a positive 1/2 spin. And the pattern repeats. All of these are -1. All of these are 0. All of these are +1. And all 3 of those columns have a -1/2 spin. -1, 0, +1, -1, 0, +1. These 3 are of the positive 1/2 type. These 3 are of the -1/2 type. So to finish out the code, the 4 quantum numbers for silicon, so third energy level 3, P sub, or the P orbital 1, the 0 orientation, because it's in this 0 column, and then the spin, positive 1/2. It is the exact same thing in the D block. Whoops. This is the D block. But there is an anomaly that we need to know about. For the D block, N, oh wait, N is equal to the rho minus 1. So for the S block and the P block, this is what I mean. So the S and the P block, for that first quantum number, I said, oh, third row down, the first quantum number is 3. Xenon, fifth row down, the first quantum number is 5. Okay, we could do that for the S and the P block. The D block is displaced by a whole row. What I mean is vanadium, row 4, it's actually the third energy level. So the rho minus 1, the third energy level. Molybdenum, it's the 5th row. It's actually the 4th energy level. So this whole block, you can kind of visualize it, the whole block being moved up a row to align it so that the energy level is correct. And then down here, in this bad boy, the F block, N is equal to the rho minus 2. So this is the F down here. Let's try one of these. Osmium, 76. Okay, we haven't done one in this block yet, but the pattern's the same. Let me get rid of my arrows because I'm going to need that space to write. Osmium, row 6, but we're in the D block, so the energy level is 5. So the first quantum number is 5. Next comes the shape. D is 2. What are the orientations for D orbitals? They are -2, -1, 0, +1, +2. -2, -1, 0, +1, +2. On repeat. -2, -1, 0, +1, +2. The amount of columns in each block corresponds to the amount of orientations available. We have more orientations available for D orbitals, so we have a wider block. Look how wide the F block is. They're the funky ones, even more orientations. -3, -2, -1, 0, 1, 2, 3, -3, -2, -1, 0, 1, 2, 3. Actually, 57 and 89 for this periodic table are still part of the D block. So the F block actually starts. Yours, the one that you're using is probably different than mine. This is not a good periodic table for this lesson, I guess. That is the F block over there. See how these go right here. Okay, so back to osmium. Row 6, N-1, energy level 5. Orientation, the shape, D, so it's a 2. Orientation, -2, -1, 0, 1, 2. We're in the -2 orientation. And then this is the second iteration of the -2 orientation. So all of these ones over here are +1/2. All of these ones over here are -1/2. So now the last quantum number for osmium is -1/2. And you thought you only had to take one foreign language. Oi. Raise your hand if you're at least 50% understanding. 60, 70, 80. Oh, I knew it. 90, 100. Okay. Okay. This is a oh man, what's going on? Okay. This is a lesson of extreme organization and patterns. So I have these pictures in here in your notes just to give you a better visual of these shapes. Okay, so we have all those in there. These are the better definition ones. Okay, here is this. This is a little shortcut tool that you could use to your advantage until you really get it down. But notice that displaced block. So 1, 2, 3. So the S and the P block are true to row. But we get down to the D block, it's row displaced. So we're in the 4th row, but it's the 3rd, right? So if we moved it all up, it would be matched up again. So this is the 1S. We call these sublevels: 2S sublevel, 3S sublevel, 4S sublevel, 5S, 4D, 5D, 6D. They're all labeled. So the sublevels are labeled for you. So in terms of quantum numbers, this table is providing you enough information to get the first 2 quantum numbers, and the last 2 you'd have to get yourself. Okay. And so the first quantum number is explicitly given, and then the second quantum number would have to be coded. S is 0, P is 1, D is 2, F is 3. Okay. So you can use this as a learning tool. You will not have access to this on a quiz or a test. Okay. This is an expanded periodic table. I keep on mentioning how the F block is actually inserted in there. They drop it down so that this fits nicely on an 8.5 by 11 piece of paper. This is what a periodic table actually looks like, a full expanded periodic table. The F block is right here. All right. We're going to get to electron configurations and orbital diagrams tomorrow. Open up your homework assignment. I'm going to have you do a portion of it. It's not going to be due in the morning, but I do want you to get a start on this so that when it is due, what we're looking at on probably Tuesday morning, we will already have some of it complete. Okay. So here we have this worksheet. We can complete this first column. That's it. That's it. That's all we learned today. Although this is a very abstract concept. You have nothing else very similar to it that you've ever learned before. I don't expect this to be easy. Okay. So baby steps. I would encourage you to watch the help video I've posted just to solidify. I'd save that for Sunday night to have like a little refresher. So you come in Monday and you're ready to go. You're still fresh with quantum numbers. Okay. So today we've learned quantum numbers. On Monday, we'll expand that. Okay. Any questions? Any questions at all? Okay, it's 12:43. We go to 12:57. That leaves you 14 minutes to get this done. Okay, so please do that now. I'm gonna go ahead and stop the recording. Online students, if you're all set, you could leave if you have any questions. You can ask them now.